Hey everybody! In this video, we are going to talk about how we can use derivatives. There's many ways they're useful. We're just going to talk about two very simple ones. So the first one is we're going to talk about finding function minimums and maximums. So suppose we wanted to find a local minimum or a maximum of a function. Well, if you find the derivative and set it equal to 0, you will either be at a minimum, a maximum, or you'll be at an inflection point. The way you tell that, you can use the second derivative. You can look at the signs on either side. I'm not going to go too much into depth on this. I just want to give you the basic idea. But so if you look here, if your derivative is 0 at this point here, and it's less than 0 on the left, greater than 0 on the right, then you'll see this is a local minimum. The function is going down, and then it starts to come back up. And at that point where it flattens out, this is where the derivative is 0, and then it starts to rise again. That's a minimum. Then we're going to come over here and look at the maximum. If on the left it's positive, it's increasing, and then on the right it's decreasing. Well, somewhere in there it had to crest the hill, and right there at the top is where your derivative is 0, and you have that local maximum there. If on both sides the sign is the same, right here it's going up and then here it's going up, at this point right here you have a point of inflection. That means it comes up, it flattens out, and then it keeps on going up. So you can use the derivative to find these minimums and maximums here. Let's talk about an example of this. Suppose you're selling coffee. You know the amount you can sell is based on the price you charge. So Q is your quantity that you sell, and the quantity is 100 minus whatever price you charge. And you want to maximize your total revenue. Revenue is price times quantity, right? It's the price you charge times how many you can sell. And you can sell based on the price, 100 minus P. So we've actually plotted this curve, this revenue curve here. And it's pretty easy to see just by looking at it that the maximum revenue you can get is $2,500 by charging a price of $50. Well, that's nice and all, but what if your function was a little harder? That's why we're using this as a simple example to see that we're right, but you can just as easily use it on a very complicated function. So we find the derivative and set it equal to 0. The derivative of this is 100 minus 2p. If you're confused about that, go back and you can either look at using the product rule, or you can distribute this out and just use the power rule. 100 minus 2p, we set it equal to 0. We then solve it and we can say, okay, well, add 2p to both sides, divide by 2. P star, the optimal p, is equal to 50. And we can see based on this curve, because it's continually, it's concave down, we can see that this is indeed a maximum point. So by setting the price to 50, we can earn that maximum revenue of $2,500. Now we're going to talk about another way, and this is using derivatives to find an instantaneous rate of change. So suppose we have a cylindrical tank, so it's like a circle on the bottom, and it just goes up and up, right? We don't know how tall it is, it doesn't matter. This tank has a radius of 20 feet, and it's filling with water at a rate of 15 cubic feet per second. What is the rate of change of the water level? So basically, we've got a hose coming into our pool, and the hose is doing its best, but we want to know how quickly is the water level rising based on the amount that the hose is putting in. So we know the total volume of water. Volume of water in this cylinder is pi r squared times whatever height we're at. And if we take the derivative of both sides, WRT means with respect to time, we can see that V prime, the rate of change of volume, equals, well, pi r squared just hangs out, that's just a constant, times the rate of change of height. And we know the rate of change of volume because there's 15 cubic feet of water coming in every second. So we want to find the change in height based on this. So we just divide by pi r squared. So the rate of change of the height, h prime, equals v prime over pi r squared, 15 over pi times 20 squared, 15 over 400 pi feet per second is how quickly the water level is rising. If we converted this to inches, this is about 0.14 inches per second. So it's kind of going a little slow. It's going to take it a while to fill up to the height that we want. But there you go. That is a second example of how we can use derivatives, how they're helpful for us. Stick around next time and we will talk about other great uses of derivatives. Thanks for watching. We'll see you later.